Hey folks, we're going to finish up with Unit 6 on work, energy, and power by looking at power in this video lesson here. So power is going to end up being our overall application of work and of energy. And what we see for power is the rate that we do work or that we are capable of converting energy. So the more powerful something is, that's because it can either do a lot of work in some amount of time compared to another object that does the same amount of work in more time, right? We can do that work faster, or we can do more work in the same amount of time, right? So like powerful motors and powerful engines, for example, right? Really, when they output horsepower, right, and they have high ratings there, it's because they are able to accomplish the same amount of work in a much shorter amount of time, right? Typically, that's what we end up seeing there. So when we do work, if we know the amount of time it takes to do work, we can figure out how powerful, right, how much power was needed to do so. Or if we know the amount of energy that was converted as well. So if we know, the kinetic energy change of a car as it's driving, we can figure out its power rating that way as well. Or if we know some height that, an elevator was lifted, for example, right? Or if a weightlifter is lifting a weight, we can figure out based on a potential energy change how much power they are able to generate, right? It's all about the idea that the work that you're doing or the energy that you're converting is then seen as a rate, right? It's the rate that we are able to do work or the rate that we get energy to convert. So power is work over time. Power can also be, as previously stated, our change in energy over time, or this even less used variation, the force times the velocity. Now, where that comes from, the force times the velocity, if you break down work is Ft cosine theta, or just Ft if we want to go in simple terms here. So because we'd be force times the displacement divided by the time, you already know that displacement over time is going to be our velocity. So you're left with force times your velocity is what we would have there. Now, looking at the unit of power, right? We measure power in watts. And the watt is defined as the joule per second. So even though we're looking at work, which can be measured in Newton meters or joules, here we see the watt when we reference work or when we reference energy as being joules per second. So as we go about this, right, the amount of power is how much work we can do per second, right? 1 joule of work per second would be 1 watt. So if you do 20 joules of work per second, that would be 20 watts. If you do 30 joules of work in 15 seconds, that would be 2 watts, right? So you're going to want to know the total amount of work done or energy transfer divided by the total amount of time. And again, because we see this as a rate, it's going to be joules per second is our breakdown on the watt. For example, and it's a pretty common example here because you all have light bulbs in your place of residence, and we're surrounded by artificial lights. If you take a light bulb that is rated at 100 watts, it uses 100 joules of electrical energy each second that it has been turned on. So because of this, a lot of LED lights now, they'll say that it's as bright as a 100-watt incandescent bulb, but it only uses 27 watts, or it uses 23 watts. And that's what the LEDs are able to do, is they're actually more efficient in their production of light. They can produce the same light output, so the same brightness, but using less energy. So the claims on those will say, yeah, this 23-watt LED bulb produces as much light as a 60-watt LED bulb. So it's using approximately 3 times less energy per second, which over the lifetime of that bulb adds up, and it ends up saving a lot of electrical energy. And that's how we save, right? That's one easy way that you can save energy is by switching over to those LEDs. Now, a little conceptual practice, right? Just kind of get the idea of power here. So if you've ever driven up a mountain road, I haven't, but you've seen it in movies, you've seen it on TV shows, or if you've been up one yourself, right? You know that they zigzag side to side across, or they go around the mountain instead of going just top to bottom. If you think about this road design, right, why is this advantageous in terms of the amount of power that is required when you relate the work that's done or the energy that you convert? So to help you out with this, right, I'm going to draw a little diagram here. So here's our mountain. Right, there's our mountain. Obviously, mountains aren't perfectly straight. So there's our mountain. And if we take our road, right, so we take a road that zigzags. So you're driving, and then you're like, hey, look, we're going to go up this mountain, right, and this road is going to zigzag back and forth until we reach whatever that highest point is. This is what is meant by the zigzag. And what is advantageous about that, rather than just driving through, and I'm going to draw this in red, rather than just driving through and then taking a road straight to the top, right? Why is the black path, the zigzag, more effective in terms of power when thinking about work and energy, as opposed to the red path, which is straight up the mountain? Take a moment, think about your answer, and then come back after you unpause the video. Okay, folks, here we go. So here's why it is more advantageous to do the zigzag path instead of straight up. When you consider going from the bottom of the mountain to the top of the mountain, you're starting at the same height, you're ending at the same height. So the vertical work that's done is the same. The mass of you or whatever vehicle you're in is going to stay the same. Gravitational acceleration is going to stay the same, and the height change is going to be the same. So because of that, the vertical work done is going to be equivalent, and if the vertical work is done as equivalent, that then means that the change in gravitational potential will be the same as well. Because remember, gravitational work is equivalent to gravitational potential energy. So because of this, regardless of which path you take, the work done is the same. So it's path independent here. Making that path longer, however, is going to take more time, because it's going to take a longer amount of time to zigzag back and forth as opposed to just, power straight up the mountain, to use, to use that term here. So because of that, if you're powering up the hill or up the mountain, it's going to take more power, right? Because you should get there faster, but the vehicle that you're in, that engine is going to be feeling it. Your RPMs are going to be really, 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 really high, meaning that you're using more power to get up there because it's going to take less time. So as you go up the mountain, the reason why it is going to be more effective and more advantageous in terms of power to take the zigzag path is going to be based on the amount of time it takes to get up the mountain. So when you zigzag, it is going to extend the amount of time that you're working, which is not going to change the amount of work done. It's going to change the time it takes to do that work. So because that zigzag path takes more time, it is going to use less power, which is going to make it easier in the long run to be able to get up that mountain. It's going to be far better for the engine of whatever your vehicle is. And when you get up there, if you were walking or biking, it's not going to require you to have to try nearly as hard because you're not moving in that straight line path, right? You get an easier path to walk or an easier path to bike or drive. If you're driving, the RPMs on your vehicle are going to be much lower because it's taking less power to get up when you zigzag. Now we'll get a little numerical practice here. So we've got an electric motor, and this motor is going to lift an elevator a height of 9 meters in 15 seconds by exerting an upward force of 12,000 newtons. How much power is that motor going to produce in watts? And I would also like you to convert that to kilowatts as well. Rationale behind converting to kilowatts is more often than not, our watt ratings can get pretty high. So using it in terms of thousands of watts or kilowatts is oftentimes a more effective way of expressing watts, even though the watt itself is the base unit. So pause the video, answer this question, and then come back. Okay, welcome back. So here's how we're going to go about solving this problem here. We're going to use our formula for power, but now we're going to be able to break down work into force times displacement because we know a force and we know a displacement. Notice even though we're doing vertical work here with mgh, we know the upward force that is exerted is 12,000 newtons. So because of that, we can just use F instead of needing mg here. Now, when we plug in our values, we have 12,000 newtons of force, we have 9 meters for our displacement, and it took 15 seconds to accomplish this. So when we write this down, this motor would be able to produce 7,200 watts of power, or 7.2 kilowatts, because we would move that decimal 3 places to the left to get watts into kilowatts. So now we've seen work, we've seen horizontal work, vertical work, we've seen angles, we've seen work energy theorem, we've seen gravitational and kinetic energy, right? Power is really where we get that application to it, where what can we do, or how long does it take us to do work or to change energy? That's where we get our power ratings from. That's where we get the power ratings for on any of your electrical devices. It comes from this right here. So this wraps up the unit on work, energy, and power. Thanks, guys.